How many people need to be in a room before there's a better than 50% chance two of them share a birthday? Most people guess something like half of 365, so somewhere around 180. The real answer is 23. Not 200. Not 100. 23 people, and the odds already favor a coincidence. This isn't a trick question, and it isn't wrong intuition either. It's a genuinely different question than the one your gut is answering. This is Symmetry. Let's find out why 23 people is enough, and what your intuition was actually calculating instead. Before the math, the question itself needs to be pinned down exactly, because there are two different birthday questions here, and they have very different answers. Question 1. How many people does it take before someone in the room shares a birthday with you specifically? Question 2. How many people does it take before any two people in the room share a birthday with each other? Nobody specified in advance. These sound almost identical, but they are completely different questions, with completely different answers. The classic birthday paradox is asking question 2. Most people, without realizing it, are answering question 1 instead, and that mismatch is the entire source of the surprise. The instinct goes something like this. There are 365 days, so surely you'd need something like half of that, roughly 180 people, before a match becomes likely. That reasoning is actually correct, but only for question 1, matching one specific fixed day. For question 2, any two people matching each other, the real number is 23. The gap between 180 and 23 is exactly the size of the paradox. This isn't a modern trick either. The puzzle was studied formally back in the 1930s, and it's been startling people at parties and in classrooms ever since, because a working demonstration takes almost nothing to set up. Any room with 23 or more people already has, on average, better than even odds of hiding a coincidence nobody planned. Teachers have used it for decades specifically because the gap between guess and reality is so large it never fails to surprise a room. The reason the real number is so much smaller comes down to what's actually being compared. It was never really about people. It's about pairs of people. With just 4 people in a room, count every possible pair you could check for a shared birthday. Person 1 with 2, 1 with 3, 1 with 4, 2 with 3, 2 with 4, 3 with 4. 6 pairs total from only 4 people. Each one of those pairs is an independent opportunity for a coincidence, and there are already more pairs than people. In general, n people produce n times n-1 divided by 2 distinct pairs. 10 people give 45 pairs. 20 people give 190. The number of people grows in a straight line, but the number of pairs grows like a curve, accelerating much faster. That mismatch, people scaling one way, opportunities scaling another, is the real engine behind the paradox. Plug in 23 specifically. 23 times 22 divided by 2 comes out to 253 separate pairs. 253 independent chances for 2 birthdays to line up, all hiding inside a room of just 23 people. Suddenly a match sounds a lot less like a coincidence and a lot more like something you'd expect. Push the group size up a bit further and the curve keeps accelerating. 30 people produce 30 times 29, divided by 2, 435 pairs, almost double the count from just 7 more people. 40 people produce 780 pairs. The people count barely moved, but the pair count nearly tripled. That's the signature of a quadratic curve. Small additions near the front barely register, but the accumulated opportunities balloon extremely quickly once enough people are in the room. Counting pairs explains why a match feels plausible, but the exact number, 50% at 23, comes from a cleaner trick entirely. Directly calculating the odds of at least one match is messy. There are too many ways a coincidence could happen. So flip the question, calculate the probability that nobody shares a birthday, which only has one way to happen, everybody different, and subtract that from 1. If there's a 40% chance of 0 matches, there's a 60% chance of at least 1. This complement trick turns a messy question into a clean, buildable one. Build it person by person. The first person can have any birthday at all, 365 out of 365, certainty. The second person just needs to avoid that one taken day, 364 out of 365 odds. The third person needs to avoid 2 taken days now, 363 out of 365. Each new person faces slightly worse odds than the last because the pool of safe, untaken days keeps shrinking. Multiply just those first 3 fractions together and check the actual number. 365 over 365 times 364 over 365 times 363 over 365 comes out to about 99.2%. With only 3 people in the room, there's still a 99.2% chance nobody shares a birthday, which matches intuition perfectly. The interesting part isn't these first few terms. It's what happens once you keep multiplying 20 more of them. Keep going, and the pattern for EN people is a product of n fractions. 365 over 365 times 364 over 365, all the way down to 365 minus n plus 1 over 365. Multiply enough of these shrinking fractions together, and the running product itself starts shrinking, slowly at first, then faster than it looks like it should. Run the actual numbers, and the product doesn't just shrink, it crosses the halfway point far sooner than most people expect. Track the running product as people join one at a time. After 5 people, it's still above 97%, almost certainly no match. After 10 people, it's dropped to about 88%. After 20 people, it's already down to 59%. No match, still more likely than not, but the gap is closing fast. Keep going 1 person at a time, and right between 22 and 23, the line gets crossed. With 22 people, the chance of no match is still 52.4%, meaning a match is slightly less likely than not. Add just 1 more person, 23 total, and the chance of no match drops to 49.3%, which means a match is now slightly more likely than not. 1 extra person tips the entire coin. There's a reason the crossing point lands specifically near 23, and it comes straight from the number of pairs. Setting the number of pairs, roughly n squared divided by 2, equal to about 365 times the natural log of 2, and solving for n gives approximately 23. The 50% mark isn't landing near 180 by coincidence of arithmetic, it's landing near the square root of 365 times a small constant, and that square root is what keeps the answer so much smaller than the day count itself. That earlier guess of 180 people wasn't a bad guess. It was a perfectly good answer, just to the wrong question. Go back to question 1. How many people before someone shares your specific birthday? Here, each new person really is just an independent roll against one fixed target day. 364 out of 365 odds of missing it, repeated over and over. Work through that version of the math, and the answer really does land around 253 people, much closer to that original half of 365 instinct. Put the two side by side, 23 people for any 2 people in the room to match each other, 253 people for someone to match one specific person. The intuition that felt wrong the whole time was actually solving the second problem correctly. It just never occurred to most people that the paradox was asking the first one instead. 23 is a strikingly ordinary number, a single school classroom, a sports team plus its bench, a typical wedding table split across 2 rounds. Almost any modestly sized group you're already part of has crossed this threshold without anyone noticing, because nobody in the room is checking all 253 pairs at once, only their own one relationship to everyone else, which is exactly the weaker, easier question with the much bigger answer. The same shrinking product math shows up anywhere you're counting collisions between pairs, far beyond party trivia. Push the same formula further. At 41 people, the odds already cross 90%. At 70 people, they cross 99.9%, essentially certain. You don't need anywhere close to 366 people, the pigeonhole guarantee, for a shared birthday to become nearly unavoidable. One more twist worth addressing. Real birthdays aren't perfectly spread evenly across the year. Some months run noticeably higher than others. Does that change the math? It does, but not in the direction most people guess. Whenever the underlying distribution is uneven instead of perfectly uniform, matches become even more likely, not less, because clustering into a few more popular days only creates more collisions. The perfectly even 365 equally likely days version used throughout this video is actually the slowest possible way for matches to appear. Real-world unevenness only tips the odds further in the paradox's favor. This exact shape of math has a name in computer science: the birthday bound. Randomly generated codes, security tokens, or cryptographic hashes collide far sooner than their total range would suggest, roughly after only the square root of the total possibilities, not the full count. It's the same pairs, not people logic driving password systems and cryptographic security today, discovered first at a birthday party. Notice the pattern connecting both problems. Whenever you're checking a fixed target against many independent tries, the count you need scales roughly with the full size of the possibility space, n. But whenever you're checking every possible pair against every other pair for a collision, the count you need scales roughly with the square root of that space instead, dramatically smaller. It's the same reason 23 beat 253 earlier, just relabeled, pairs versus one target, over and over, in whatever space you happen to be searching. Once you know to look for it, this exact shape, pairs beating a fixed target by an enormous margin, turns up far outside of birthdays. So 23 people is enough, not because coincidences are common, but because 253 pairs are hiding inside those 23 people, each one an independent chance to match. The gut instinct chasing half of 365 wasn't wrong, it was just answering a different, harder question than the one being asked. A fixed target instead of any pair at all. Once you start counting pairs instead of people, the same shrinking product math shows up everywhere. From party trivia, to how quickly hash collisions appear, to any system quietly built on checking every pair against every other pair. If you want more ideas like this explained from first principles, subscribe, Symmetry. See you in the next one.